Thank you for the invitation to talk at this conference. It's always a great honor and a pleasure. I'm going to talk about superconformal theories in dimensions higher than 4, and in particular about their gravity duals. And my talk is mostly based on papers I wrote with Abruzzi, Fazzi, Rosa, who's my student, Gaiotto, and Pasias. There are many reasons you might be interested in this topic. One is just that it's an interesting, nice theoretical issue. For example, if you just naively start with a Yamis, as you're used to in other dimensions, well, that won't work. This will be strongly coupled in the UV. String theory, of course, suggests many ways to solve the problem, to go beyond it, such as by introducing non-abelian tensor fields, as for the theory living on the Word volume of M5 branes, which is one of the open problems in the theory. So that's interesting too. And also we have learned over the past few years that these theories give rise to interesting theories also in 4 dimensions and fewer. Today we're going to see some classification results for theories in higher dimensions, especially 6, using ADS-CFT. Here's a quick preview. First, we are going to see a classification of ADS-7 solutions in type 2 supergravity. In 11 dimensions, it's easy to see, actually, that there is only ADS-7 tensors 4 up to orbifolds. But in 2A, actually, there is also the possibility of switching on the so-called Romans mass, which is just a Ramon-Ramon flux with no indices. And this would be an interesting story to discuss, but basically the presence of this parameter prevents lifting to 11 dimensions. And so we have to start with a new classification, and it turns out that there are many new solutions where the internal space is topologically a trisphere, but its metric is distorted in a certain way that I'll discuss. I will then present a proposal for what the CFT duals are. This will be 1,0 CFTs. And I'll basically argue that the theories, or actually that the ADS solutions arise as near-horizon limits, of brane intersection like this, brane system like this, which was already studied in the 90s, actually. I will also comment towards the end on the relationship of these results with those presented by Vafa on Monday. Finally, I'll show you the beginning of a similar story for ADS-6. So the plan is first to review very quickly, don't worry, the methods that we used to arrive at these results, and then I'll discuss the 3 topics I just introduced, I just previewed for you. So the methods sometimes go under the name of pure spinors. I'm not sure if this is the best name, but they are especially well suited, whatever they should be called, they are especially well suited to the case of type 2 supergravity, where there are 2 supersymmetry parameters. In general, when you have 1 supersymmetry parameter, you are tempted to trade it for a set of forms or tensors, perhaps, with the same little group G, and this is sometimes called the G structure. But if you have 2 supersymmetry parameters, then you have complications, because the 2 may have different Gs, and also you have to keep track of the various ways that they can intersect with each other. And that gives rise to, well, a mess. But there is a better way, which is to work with the so-called, I would call it generalized tangent bundle, which is the direct sum of the tangent and cotangent. It kind of deals with vectors and one forms at the same time. It puts them on the same footing. And ideologically, an advantage of this is that you don't have to introduce the metric until very late in the game, basically because this bundle already has a natural pairing. And practically speaking, that gives rise to nicer equations and to easier classifications at the end. In some situations, the forms realized in this structure, in this bundle here, can be realized as pure spinors, can be understood as pure spinors for this bundle, hence the name of the method. Now, well, it's important to stress that in spite of the name, I'm not the space is actually still geometrical. These are all geometrical. I'm not messing with the manifold in any way. It's just a different way of doing ordinary geometry. Now, the original example was for compactifications to 4 dimensions. I actually presented this at this conference many years ago in 2005. And in that case, the internal space carries a SU3 times SU3 structure. This is what G is. And that makes contact also with the so-called generalized complex geometry defined by Hitchin in 2002. In 2011, I found an extension of this formalism to any 10-dimensional space without necessarily assuming such a factorization, or any factorization for that matter. This is the main equation, which I will not actually explain, just pictorially there. But there are actually more equations which are, however, in most situations, redundant. The price to pay is that you have a seemingly more complicated G structure, but the reward is that you can now apply to many other situations, such as the ones that we are interested in today. Now, for this case, for example, the main difference is that the internal space carries what I would call an identity times identity structure, rather than SU3 times SU3. Well, what is an ordinary identity structure? What is a set of forms whose leader group is the identity, just nothing? Well, it's a basis of one forms, otherwise known as a Vielbein. So actually, this guy in the generalized case corresponds to 2 Vielbeine, which are loosely associated with the left and right movers of the string. But, well, it proves more useful to actually work with some kind of average of the 2, and also with some kind of, I would call them Euler angles, which are some data parameters that parameterize the local Lorentz transformation that goes from one to the other. These are actually functions on the internal space, and this will be important. Now, after this general discussion, let's see how all this applies to the case of ADS7. Let's start with 2B. I'm not actually showing you the system, but if you look at it carefully, you immediately realize that there are some equations which are particularly easy. They are zero-form equations. They are algebraic, and for the Euler angles we were talking about just now. And, well, it's a second's work to see that there are no solutions at all. So, well, this is one of the first rewards of this fancy mathematics. You get very clear results. Now, this is, I should stress that this is really for perturbative 2B. F theory goes, of course, beyond perturbative 2B, and we will see that there's a nicer story there. Now, let's go to 2A. In this formalism in general, 2A and 2B are not really that different. Formally, the system looks the same. What changes is the degree of the forms involved. And in particular, now we don't have zero-form equations anymore. We rather have one-form equations. These are the simpler equations we can find. And what they do is the following. They determine the Vielbein in terms of derivatives of these functions, of those that I call the Euler angles. So in particular, well, then it means that you have directly, without any ansatz, directly the local form of the metric. And it looks like this. It's a S2 fibration of a one-dimensional space, which will turn out to be an interval. And intuitively, the metric on the S2 is the round one. And intuitively, this is because there has to be a realization in the metric of the R-symmetry of a 1,0 theory. If you then look at the rest of the system, what it does is simply that it determines the fluxes for you. There are no further geometrical conditions. And it turns out also that they obey automatically away from sources the Bianchi identities and the equations of motion for the fluxes. So when, at the end of the day, what we get is a set of 3 ODEs, one for the volume of the two-sphere, one for the warping function. So in particular, these are always going to be Worth products, and one for the dilaton. As a warm-up, let's see what happens in the massless case for zero Romance mass. Well, in that case, we might as well start working with 11-dimensional supergravity. By symmetry, you can see that you need to take a Freund-Rubin, so-called Freund-Rubin ansatz, where the flux is taken to be completely along the internal space. And with a few steps, you can see that that means that the cone over M4 should have reduced holonomy. That's a 5-dimensional space, and there isn't much you can do. It's basically just flat space up to orbitals. It's kind of sad, which means that M4 itself is the up to orbitals again, the 4th sphere. So we end up with this well-known solution. Can we reduce it to 2A, which is our real topic? Yes, it can be done. You have to realize S4 as follows. You realize it as an S3 foliation. And now on each of the S3s, you have the so-called Hopf fibration that realizes it as a S1 fibration over S2. And now, if you now reduce along those S1s, you end up with the S2. In type 2A, you end up with the S2 foliation, where the S2s only now, they don't shrink to 0 at the ends of the interval in a regular fashion, but they give rise to two singularities that, upon further reflection, can be seen to be corresponding to the presence of a D6 and of an anti-D6. That's actually to be expected, because here the S1, the vector field you were reducing along will have two, necessarily by topological reasons, will have two zeros. And actually, something I didn't mention is that this can be done supersymmetrically, so you only break half supersymmetry in this way. If you work a little harder, you can see that everything is in perfect agreement with the system of ODEs I mentioned in the previous slide. Now let's see what happens for non-zero Romance mass. The first thing we can do that we couldn't do before is to make one of the two poles where we had the singularity a regular point now. This, practically speaking, becomes a certain boundary condition for the system with of ODEs that I mentioned. And it's a first-order system, so you don't have, you can't make any choices anymore, and you end up with this teardrop-shaped solution which has a single singularity now, which represents again a D6. Now, we can do something even better. So since there is F0 in the game, we can include D8s, which after all are just sources for F0. They are the loci across which, if you cross them, F0 jumps. And now, well, you start with, again, as before, but supersymmetry dictates at what radius, at what value of the radius you can place the D8 brane. Actually, I should improve my discussion here. Let's say I also allowed for a worldsheet flux on the D8s, and so worldsheet F2. And that just means that we are considering more generally a D8, D6 brane, a D8, D6 bound state. So we're saying then the supersymmetry tells you what radius you can place it. And once you cross it, the system of ODEs changes because it depends on F0, and F0 has jumped. So the evolution changes a bit, but if you tune things just right, you can obtain that the other pole is regular as well. And here is actually the actual numerical solution for this case. This is, of course, just a cartoon. I chose to show cartoons all over because I thought they would be clearer. But the numerical solutions are available upon request. Now, you can do something more complicated. You can also, here I have included two D8, D6 bound states, and they have opposite charge. And this one is particularly intuitive to me because it looks like a balloon with two rubber bands pressing on it. And they would tend to slip towards the poles, but they're actually also electrically charged. And they have opposite charge, and they attract each other. So the whole thing is stabilized. Now, well, you can keep going. So you can also introduce more D8s. You can have fun. You have to, basically, the data that you have to give me to produce such a solution are the numbers of D8s that you want to place, and there are D6 charges. And they will organize in several stacks on your space, which is topologically a trisphere, remember? And also, you have to specify the flux integer for the Nair-Schwartz tree form. You cannot choose these parameters just as you like. There are some constraints. to tell you what the first is, I have to confess that this mu I just was talking about actually depend on the gauge choice for the B field. Much like for, we have to place a gauge transformation for the B field somewhere, a bit like for the Dirac monopole. And we can choose to place it, for example, in the region where F0 equals 0, which is generically present. And in that case, the constraints look like this. The mu i's are positive and growing as you go towards this region for F0, positive and negative and growing towards 0 for negative F0. Well, intuitively, the D8s with the bigger positive charge are more attracted to the negatively charged counterparts on the other side. So this is the explanation of this constraint. And we can also summarize it by, if we want, for fun, now it's just for fun, we can assemble these mu i's into two Young diagrams. And then, by the way, I can also picture for you the second constraint, which says that the flux integer n should be bigger than the sum of the two tallest columns for the two Young diagrams. Finally, we should also make sure that the n and the ni's are all large enough so that we are in the supergravity approximation, so that the curvature and dilaton are small, but this can be done pretty easily. Now, this was the classification of the ADS7 solutions. Let me see whether I can find the CFT duals. A common strategy is to look for a brane configuration whose near-horizon solution reproduces your ADS solution. And this can actually be done pretty easily for the massless solution as follows. Here it is again. Actually, I have generalized it just a bit by introducing a ZK orbifold, which results in the presence of k d6s rather than just one, and also k anti-d6s on the other side. And this actually now is the near-horizon limit of something, namely of M5 branes at the ZK singularity. Now we can close the square by reducing to 2a directly from here. And what we find is a configuration like this, with the NS5s on top of d6s. Now, the near-horizon limit of NS5s is not ADS7, and neither is the near-horizon limit of d6s. But somehow their intersection does produce in the near-horizon limit the desired ADS7. And so these are the degrees of freedom that we are actually interested in. And they are described by a theory with 1, 0 supersymmetry with n cubed k² degrees of freedom. Now, let's see whether we can also include the Romans mass. It stands to reason that perhaps we should also introduce the 8 branes somewhere, because those are the sources for F0, as I already mentioned. Here's the simplest possibility. We can have each of the d6s end on a separate d8. And, well, this was found by Garrett and Witten in a different context to correspond to placing Dirichlet boundary conditions on the fields living along the d6s, thus isolating for us the degrees of freedom of this defect here. If you want a more general configuration, you can now have some of these d6 segments slide off towards infinity. This is a natural interpretation of somehow as a RG flow towards now a new theory describing this brane configuration. Notice that I'm keeping the NS5s on top of each other. I will later comment about this. But now you might be tempted to take directly the near-horizon limit, as I did before, towards this intersection. But a worry is that this might just wash away the d8s so that you end up with the previous solution, the massless solution. However, I would argue that this is not the case, basically because the d8s should be actually thought of better as nonpoles for the d6s. What that means is that the BPS equations on the d6 are the NAM equations, and the presence of a d8 just corresponds to the presence of a nonpole whose residue is actually, well, parameterizes an SU2 subalgebra of the gauge group, which can be summarized in a Young diagram. And the Young diagram is actually related in an intuitive fashion to the naive brane picture here. This is also inspired by this paper again. Now, so the bottom line is that a better picture, rather than this, is something like this with fuzzy funnels coming out of the bunch of NS5s. So now it becomes more plausible that if we take a near horizon limit near this region, the D8s are not washed out by the limit, but they remain and they become the D8, D6 bound states that we had before. More precisely, I would conjecture that the number of D6s ending on a D8 becomes the mu charge that we had before, and the number of NS5s will become the flux integer that we saw before. Now, putting the NS5s on top of each other suggests that, I mean, this looks like a good way to get a CFT, for example, because you should get tensionless strings in this way. But a finer analysis shows that there should be constraints. One was again found by Gerton Witten. It says basically that the D8s with a bigger number of D6s, in this case, should be standing on the left of the others. And another one has to do with the fact that if you start separating the NS5s in order to reach an effective description where you have actually something more like a quiver, well, if you don't have enough of them, you'll get some extra free hypers that look like they would spoil the presence of a CFT. So now, applying the map that we saw before to this configuration in the previous slide to these two constraints, we get exactly the two constraints that I showed you for the ADS7 classification. So I would claim that there is a one-to-one correspondence between the CFTs and the ADS7s, and we're all happy. So this is some kind of evidence in favor of the conjecture. Well, if you want, this is the main message, but let me quickly show you a couple to codas. One is this, a comparison with the Waffer's talk. Well, they were considering D7s, which are non-perturbative, and they were intercepting each other in some kind of chain. And, well, what is the relationship? Well, something you can try is just to T-dualize along a direction transverse to the D6s, which turns them into D7s. And these are also becoming D7s now. But the experience shows that if you have a configuration like this with the D7s intercepting each other, well, most probably they fuse into a single entity. And this looks now very similar to their chains of S2s, except now there are these two strange things at the end, which I would interpret as being described by hitching pole, which is just a T-dual of the non-pole that we saw in the, a couple slides ago. So this suggests that the classification in this paper should be decorated by adding hitching poles, and we are currently exploring this possibility. Also, it's interesting to notice that some of their chains, especially this repeated pattern here is especially interesting, are dual to ADS7 solutions, such as this guy. So let me end now with a discussion of the ADS6 case very quickly. Now the role is reversed. 2A doesn't have any solutions for the F0 equals 0 case, and it only has one for the massive case, which represents a bunch of D4s near the 8 or 8 wall. This was found by Banduber and Oz and proven to be unique by Passias. In 2B, we have evidence, we have analyzed completely the situation with using the same methods that I discussed at the beginning of the talk. And again, without the need for any ansatz, we find the most general form for the metric. And it looks now as follows. It's an S2 fibration of a two-dimensional space. And again, the fluxes are also all determined. And they obey the Bianchi identities automatically. So again, we have reduced completely the problem to a set of first-order equations. Only now there are PDEs, and there are PDEs on this two-dimensional space. And right now, there are only two known solutions. However, these were also obtained by T-duality and by non-abelian T-duality, which is a solution-generating technique from the solution in massive 2A that I mentioned earlier. But I think there's a general story awaiting here, which should look as follows. There should be many new solutions of these two PDEs, which should correspond to now PQ webs, PQ fibrine webs, ending on PQ7 branes. These configurations have been indeed studied in the context of CFTs. And it will be interesting to find a solution corresponding to those. Well, finally, my time is up. So here are my conclusions. In one sentence, we find the gravity duals, 1,0 gravity duals for a large class of 1,0 CFTs labeled by an integer and 2 Yann diagrams. And there are generalizations I didn't discuss involving O6s and O8s, hints of a more general story coming from F-theory, and also probably a similar story for 5-dimensional CFTs. Thank you.
Thank you very much, Alessandro. We have time for questions.
The pure spinor equations for the ADS7 solutions, to what extent are the two unpleasant pure spinor equations redundant?
To a full extent. So for all these configurations, when I said that they're almost, I don't remember what exactly I said. Let me see if I can jump. So here I mentioned that there are some more equations which don't look as nice as this one. Well, perhaps many people here don't think that even this one looks nice, but believe me, if you have some experience, it does. And they are redundant for this case, also for this case, and also for this case. They are non-redundant for very exotic cases. No, I wouldn't call them exotic. But for example, we tried to apply them for situations where you had an arbitrary 4-dimensional metric here in the 4 dimensions times an arbitrary 6-dimensional metric. And now those are not, those slightly more unpleasant equations are not redundant. And this is in collaboration with Dario Rosa, my student.
Any other question? Any questions from the balcony?
Is there a solution before taking the near horizon limit of those brane systems? Will that be very, very difficult compared to this analysis?
Short answer is no. I mean, if you mean the general case, the answer is clearly no. These solutions here, I don't have solutions before the. So, okay, maybe thanks for the question. So perhaps I will be able to be much clearer. So the identification is based, it looks like it's correct. I mean, there are several things that make me think that it's correct, but that doesn't mean that I actually have the supergravity solution before. With one exception, in the massless case, in this case here, well, I mean, since I know this metric here, I can also reduce it. However, if I'm really lazy, the solution, so this solution describes this brane intersection. Brane intersections are notoriously difficult to, if you want to, the sources to be localized. But it's easy to get a solution which will be valid in the vicinity of the D6s and at any distance along this direction. So that I can do easily. And I think perhaps it can be also done fully. But in the general case, no way.
Thank you. So let's thank Alessandro again.